After a bachelor's at Johns Hopkins, she came to UCLA, where she managed to pick off all 4 of the graduate student prizes, including the Bjerknes for research, the Nyberger for teaching, and the Bozart for service to her fellow grad students, as well as the UCLA-wide dissertation award. When she finished her PhD, she went to JPL for a postdoc, which I think she's going to touch on things that she's continued from there in today's talk. And she's an assistant professor at University of Virginia now, working on things related to clouds, convection, and precipitation. So, Kathleen?
Okay, yeah, thanks, David. Thanks, everyone. Great to be back. Great to see so many familiar faces. Akio has had quite an impression, of course, on me and my work, and I remember as a grad student seeing him walk very slowly down the hall past as I was in classes, and was always in awe. Always too shy to walk in his office, but always in awe. And was hoping that at one point in my career I would have as much love and dedication and connection to my work as he has and had throughout his career. So anyway, there are many things that I could touch on that I've been a part of and had the pleasure of working on over the past few years that connects in very many ways to Akio's contributions. But today I chose to talk about one particular study that I've been working on recently that connects the model spread in the tropical low cloud feedback to the overturning circulation response to warming. And a lot of what has motivated this work is my interest in understanding how low cloud feedbacks tie to deep convection, because we know how important deep convection is to the tropical atmosphere as a whole in its entire thermal structure. And looking across the CMIP ensemble, how some of the intermodal spread in low cloud changes may relate to different intermodal spreads in the way that deep convection is affecting the tropical atmosphere. So we know that the tropical low cloud feedbacks are a root cause of uncertainty in the strength of the total cloud feedback and ECS. And so this is just from Mark Zelinka's recent work illustrating that ECS is expanding in its range. And I am not the first to show this, but this is from a recent study where I have been looking at the relationship between low cloud fraction in the subtropical regions, which I'm loosely defining as wherever omega is positive. The low cloud fraction here on the x-axis in the right panel is for descending regions only, and that relates, of course, quite strongly to the intermodal spread in the CMIP6 ensemble in the net cloud radiative effect. And so thinking about how deep convection and its effect on the thermal structure, and we always talk about how deep convective parameterization is such a contributor to intermodal spread in both circulation fields, cloud fields, but what really are potential implications of inadequate observational constraints and incomplete representation of convective processes in GCMs for future climate? And more specifically, how do deep convective processes in the ascent region affect dynamic and thermodynamic controls on low cloud populations across the tropics? And their changes. So physical connections, of course, between deep convection and low clouds through the circulation, through the stability of the atmosphere, and through changing the humidity structure, the tropical atmosphere, and of course these are all interrelated. And so I'll touch on all 3 aspects of this throughout the talk today. So this is from a nice paper by Greg Sassana and Tony Del Genio recently looking at actually observational constraints on low cloudiness, but these are looking at large intermodal differences in the shortwave cloud radiative effect among high and low ECS models. So in the top, this is a composite of the net shortwave cloud radiative effect for high ECS. In the middle, it's for low ECS, and all ECS in the bottom. And so you can see that some of the intermodal spread is, of course, coming from key regions of interest over the last decade or two that have received a lot of attention in LES studies and observational work, the stratocumulus regions. But there's also a lot of a contribution among high and low ECS models in terms of differences in convective margin regions and in trade cumulus regions. And wondering, of course, because they're on these deep convective margins, how closely associated changes in deep convection or ITCZ width and structure may relate to the intermodal spread and low cloudiness directly. So this is another composite of high and low ECS. So on the left, this is the left column of high ECS composites, and the right column, this is for low ECS. And in the top row is showing the change in the high cloud fraction per degree warming. So in high ECS models, there's a really strong decrease in high cloud fraction per degree warming in comparison to low ECS models. And unsurprisingly, there's quite a large difference among high and low ECS models in the low cloud fraction as well. And if you look at pattern changes, a lot of in the net cloud radiative effect in the bottom, for high ECS models and low ECS models, that largely reflects where the changes in the low cloudiness occurs. But there are very distinct differences in high ECS and low ECS models in terms of the high cloudiness and how interrelated are high and low cloud changes. What are potential physical mechanisms that could relate high cloudiness and high cloud changes to low cloudiness and low cloud changes? So first, doing a little bit of a survey of how the tropical ascent region is changing under warming in the CMIP ensemble. So Fayez showed this before and nicely connects back to some of his work, where the tropical ascent area is reducing in many climate models, and the frequency of heavy precipitation is also increasing in many climate models, and I'll quantify that in a moment. And so these changes to deep convection end up resulting, and I'm showing that to the right here, resulting in less detrainment of water vapor and condensate. So in the right, on the x-axis, this is a change in the ascent area fraction. So taking any grid box that's going up and looking at that response to warming. And the change in the high cloud fraction in descent regions in particular. And this actually, this correlation, this is probably the lower of the correlations that emerges from any bit of this ensemble I pull out. But this is, CMIP 3 models show the same thing, CMIP 5 models, this is just showing CMIP 6 models, and in other model ensembles. And so I would have no reason to not believe this. And so the change in the ascent area fraction is closely related to high cloudiness and high cloud reduction. And there's also, across the CMIP 6 ensemble, I've been trying different ways of classifying changes to heavy precipitation. And so I came up with this somewhat arbitrary metric of just a frequency of precipitation greater than 10 millimeters per day, looking at monthly mean data. And so that's on the x-axis in the bottom here. And that ends up across the CMIP 6 ensemble relating to the intermodal spread in the relative humidity at 250 millibars in the descent region. And so illustrating that changes to the tropical ascent area and ITCZ narrowing across the CMIP 6 ensemble in particular seems to relate most closely to the change in high cloud fraction. But then there's also, if you look at the change in the frequency of heavy precipitation, that relates to detrainment as well and upper tropospheric relative humidity across this ensemble. And so changes to deep convection end up resulting in less detrainment of both the water vapor and condensate. And one thing that I found quite surprising at first was that a smaller tropical ascent area, so as we just saw, which relates to fewer high clouds, is seen in models with higher ECS. And I kind of expected the opposite at first, and I'll explain that in a moment. More frequent heavy precipitation, which as we just saw a moment ago across this ensemble, relates to lower upper tropospheric relative humidity, is also found in models with higher ECS. So kind of in exploring these relationships, I was thinking, well, first of all, shouldn't reduced high cloud fraction and upper tropospheric relative humidity lead to a negative long wave cloud feedback and promote lower ECS, not higher ECS? And then I thought maybe about low clouds, and how high cloudiness and high cloud reduction may relate to low cloudiness and low cloud reduction. So first, taking a step back and seeing how the overturning circulation is changing under warming. And by the overturning circulation, I mean we've already touched on the ascending branch, now touching on the descending branch. So subsidence weakening in the subtropical regions is generally more pronounced in low ECS models than in high ECS models, which hopefully you can see, though the colors are not coming out perfectly here, and highlighting in both the north, south, and east-west composites this exact same idea, where in the high ECS models you end up having less subsidence weakening. So how does subsidence relate to low cloudiness? Well, actually, stronger subsidence generally disfavors low cloudiness in the presence of a strong inversion, a la Myers and Norris. And so when stronger subsidence is preserved in the future, or there's less weakening, this ends up promoting a greater reduction of low cloudiness. And so that is consistent with what I'm showing here. So on the x-axis is the change in omega 500 in the descent region. You can see that that's negative, so we have a weakening. And the change in the low cloud fraction in the descent region. So if we have more weakening, we have an increase in low cloudiness, or less weakening or stronger circulation is preserved, and we have a greater reduction of low cloudiness. Now, whether or not that is a direct effect of the dynamical effect of the subsidence, or whether it's the subsidence affecting the thermodynamic structure, which would affect the low cloudiness, is a bit to be determined. But in correlating, for instance, the omega 500 here with the change in the relative humidity at 700, you can see that, if you have a greater increase in subsidence, you have a greater decrease in the relative humidity. And so there's potentially this, we think that the contribution, this relationship that we showed in the previous slide, may in fact be largely to do with the effect of subsidence on relative humidity, which is a pretty uniformly strong and same sign relationship across the tropics. And one other thing I want to point out is when I introduce a few physical mechanisms in a moment relating high cloudiness and circulation to low cloudiness, I want to point out that the strongest relationships locally between subsidence and low cloudiness seem to be more along these convective margin regions. So the mechanisms I talk about in particular in a moment are going to be, we think, more applicable to regions of along deep convective margins, as opposed to controlling stratocumulus cloud fraction, for instance, in stratocumulus regions. Okay, so subsidence relates to, intermodal spread and subsidence relates to the intermodal spread and low cloudiness across the CMIP6 ensemble, interestingly. But what controls the subsidence rate and its changes under warming? Well, in the absence of horizontal temperature gradients or latent heating, the energy balance of the free troposphere is given by the radiative cooling and the adiabatic warming by subsiding motions. So increasing radiative cooling, you increase subsidence. Decrease tropospheric stability, you increase subsidence. So I want to look at both of these aspects. We'll start with radiative cooling to see how that relates to the change in the circulation. So in panel A, this is showing that the intermodal spread in the subsidence rate is strongly linked to the intermodal spread in changing outgoing long wave in the descent region. So x-axis is the subsidence rate, y-axis is the change in the OLR. And the intermodal spread in OLR in panel B is explained by changes in high cloudiness, which relate to the ascent area fraction. So decrease ascent area fraction, decrease high cloudiness, increase outgoing long wave. And then in the bottom, not ignoring the vapor, so upper tropospheric relative humidity changes on the x-axis here. If upper tropospheric relative humidity decreases more, that also leads to an increase in outgoing long wave. So changes to the ascent area fraction can affect high cloudiness. Changes in frequency of heavy precipitation in this ensemble appear to be quite related to the change in the upper tropospheric relative humidity. Both of those changes increase outgoing long wave, and that increase in outgoing long wave ends up relating quite strongly to preserving stronger circulations. So we call this the radiation subsidence pathway, whereby a reduction of tropical ascent area and more frequent heavy precipitation leads to relative humidity reduction in the upper atmosphere, high cloudiness reduction. That increases the outgoing long wave. There's then less subsidence weakening, or there's stronger circulations preserved, and a greater low cloud fraction reduction. Again, we think that this sort of mechanism might be acting more strongly along convective margins rather than explicitly controlling stratocumulus regions, or at least it seems that way when we look at composite maps and looking at correlations. So if we go to the stability aspect, a couple of interesting things emerge. So the first is the intermodal spread in tropospheric stability, so on the x-axis in the top panel, is very closely tied to the intermodal spread in the subsidence rate, so that makes sense. We expect that. But looking, for instance, so the changes in stability are not independent of OLR and are likely driven in large part by the changes in the radiative heating, so putting that out there. So this is kind of an extension on what I just presented, the radiation subsidence pathway, whereby we have the tropical ascent area reducing, more frequent heavy precipitation, and our stability increases less. And that also relates to the increase in OLR. So that, again, leads to the less subsidence weakening and the greater low cloud fraction reduction. Another interesting thing that emerges is, well, what about the mean state static stability? Deep convection and intermodal differences in deep convection can relate quite strongly to intermodal differences in static stability. So that's what's shown in these two panels. So this top panel is just showing that there is the intermodal spread in the mean state stability is closely tied to the intermodal spread in the change in subsidence rate. So stronger subsidence in the mean state ends up having stronger circulations preserved, or you have a smaller change in the circulation. And on the bottom, this is showing that some metric, again, that I kind of arbitrarily made up of a fraction of precipitation greater than 10 millimeters per day, using that as a metric of a frequency of heavy precipitation as best as I could with monthly mean output. That is quite varied across the models, and that relates to the static stability of the tropical atmosphere. So when a model ends up, for whatever reason, due to its parameterization or other aspects, having a greater F of heavy precipitation, that ends up making or having a model with a more stable troposphere. And so this is one way of illustrating intermodal differences in deep convection and deep convection parameterization and how that relates to mean state static stability, which can then feed back onto or affect how the circulation changes under warming and how cloud feedbacks may behave. So let me kind of ask, well, what could control mean state static stability differences among models? And pointing some figures at entrainment. So on the left here in panel A, this is looking at the static stability on the x-axis and the mean circulation on the y-axis. These are in parameter perturbation ensembles in CAM 5.3. The values 1 through 5 are increasing entrainment, 1 being the lowest value and 5 being the highest. And so if you increase entrainment, you end up decreasing mean state static stability in the atmosphere, and that ends up relating to stronger subsidence. So decreased stability, stronger subsidence. You can also see that that reflects in the way that omega 500 relates to low cloud fraction in the mean state. Here I'm just showing the mean state, where if you have higher entrainment, you end up having a stronger circulation because you're less stable and your low cloud fraction is reduced in these parameter perturbation ensembles. So that's similar to what I was illustrating before across the CMIP6 ensemble, but putting a little bit more of an emphasis on what particular processes within GCMs, like entrainment, could potentially contribute to an intermodal spread in tropospheric stability that could affect the circulation and low cloud feedbacks. This is another nice illustration contributed by Fayaz looking in higher frequency output, where higher entrainment means, so showing on the left panel, this is for the low entrainment case, where lower tropospheric subsaturation is on the y-axis, or x-axis, and on the y-axis is the lower tropospheric instability. The colors are different precipitation rates. Again, this is from a parameter perturbation experiment in CAM5. And the maroon contours are the precipitation PDF of precipitating points, and the star is for the mode of that PDF. And so you can see that higher entrainment means convection needs a more unstable environment in order to fire due to the enhanced sensitivity of convection to lower tropospheric moisture. And so kind of illustrating that, more precisely illustrating how entrainment can affect stability and how that connects to low cloudiness. So a few additional thoughts in addition to the summary. So in summary, first, the tropical ascent area is reducing in many models, and there's more frequent heavy precipitation in many models. That leads to relative humidity reducing in the upper atmosphere, high clouds reducing, and stability increasing less, and the stability relating also to increases in the outgoing long wave. This all leads to, we think, less subsidence weakening and then affecting the low cloudiness by reducing low cloudiness more. So greater reduction of high cloudiness, greater reduction of low cloudiness, and we think that that has to do with the changes in the circulation. But these are only two mechanisms that emerge as contributing non-trivially, perhaps, to the intermodal spread in ECS. And both mechanisms connect deep convection changes to the low cloud feedback through changes in high cloudiness. But they're not the only mechanisms. And for the sake of encouraging discussion about potential other mechanisms, there are many. For instance, one that I've been looking at in a couple of different simulations is lower tropospheric stability changes. So throughout the talk, I've been talking about the entire structure of the tropical atmosphere, not necessarily lower tropospheric stability. But if we do talk about lower tropospheric stability, we know that's a major player in terms of controlling locally, especially stratocumulus cloud fraction. And this could be related to tropics-wide changes in OLR or latent heating, not necessarily connected at all to changes in subsidence rate. It could be a more direct effect of changes in OLR and changes in latent heating. And so this is a set of experiments that I pulled off of the CFMIP archive, which is just looking at long wave cloud radiative interactions turned on and off. And so on the top, this is the outgoing long wave difference between the long wave off and long wave on experiments, as we call them. The lower tropospheric stability difference between the long wave on and long wave off experiments, which you can see that the change in the stability, particularly over stratocumulus regions, is really quite large. And that corresponds to a pretty large difference in low cloud fraction. And so increasing OLR, in this case, you can see very, very strongly, because we're turning off that interaction, disabling that interaction. This is perhaps, an overdoing it case. So the lower tropospheric stability decreases quite a lot, and that decreases the low cloudiness very substantially. So this would be a much more muted scenario in the case if we're just looking at changes to high cloudiness due to ascent area fraction reduction or other changing characteristics of deep convection across the tropics. But for instance, this could be a way of connecting deep convection and changes to low cloudiness, or changes to high cloudiness, to changes to low cloudiness, but not necessarily connected to changes in subsidence or changes in the overturning circulation. And so that's something that I'm quite interested in exploring a little bit more and looking at. And perhaps in a more realistic experiment in a similar vein. So in the top, this is an experiment that I did a couple of years ago and revisited some of these runs, where on the left, these are composites for high cloud fraction, and on the right, these are composites for low cloud fraction. These are parameter perturbation experiments, but instead of perturbing deep convection, I've perturbed microphysics, and in this one particular case, I perturbed the stratiform ice fall speed. So in the top, the stratiform ice fall speed is faster. In the middle, the stratiform ice fall speed is slower, and then the bottom is fast minus slow. And so you can see that when you decrease the amount of ice, you also, you decrease the high cloudiness, and there's a corresponding decrease in low cloudiness. And so playing around with and trying to understand whether that is related to circulation changes, whether that has more to do with direct changes to lower tropospheric stability or other thermodynamic effects to the lower free troposphere is something I'm quite interested in exploring a little bit further. So I think I'm out of time, and if anyone has any feedback or ideas for future exploration of some of these mechanisms, I'd be really interested to hear. Thank you.
Questions?
Yeah, I actually have two questions. The one is for both you and Fayez talk. Both of you talked about the changes in the active rain parts and the dry descending region. And is there? Do we know which one changes in which side happens first? And the second question is, can you explain a little bit more why the relative humidity decreases when the strong precipitation events increase?
Yeah. So great question about which happened first, descent or ascent. And I think speaking about causality, I'm interested in deep convection and how that affects the thermal structure of the atmosphere and the circulation. So I'm trying to make a connection from deep convection to subtropics. But also low cloudiness can affect circulation and the thermal structure, and so it can all go the opposite direction too. And yeah, so it's kind of interesting to think about what causes what, and I think mechanism denial experiments could help a lot with that, though must be carefully constructed and must be carefully thought out. Very difficult to think about how to construct a couple of mechanism denial experiments, for instance, to explore future this stuff in future work. And in terms of the relative humidity, I think you may have been talking about the relationship between the upper troposphere and subsidence, yeah. And so we think, well, at first, to kind of go back a little bit before answering that, when I think of low cloudiness and the changes in low cloudiness, I always think about lower tropospheric stability, relative humidity at 700, and in the boundary layer, differences between the boundary layer and lower free tropospheric relative humidity, and not as much subsidence because it doesn't seem as seemingly strong of a meteorological control in observations. And so I was a bit surprised to see the relationship with subsidence and low cloudiness. And then when I was looking a little bit more strongly at, for instance, how the subsidence related to estimated inversion strength or relative humidity, and I guess I didn't show the estimated inversion strength here, it started to make a little bit more sense that maybe the subsidence itself related to the relative humidity. For instance, like if you have more air coming from the upper troposphere and greater drying, or changing the estimated inversion strength in the lower atmosphere. And I think that the estimated inversion strength, which I didn't get to show, and maybe I'll spare you, but I think that the estimated inversion strength is a stronger control in the stratocumulus regions that I think maybe some of these mechanisms with the high cloudiness don't necessarily relate to as strongly, meaning if EIS is most closely related to low cloud fraction in those regions, then it's probably not coming in as much as, for instance, relative humidity on convective margins. But yeah, so some additional thoughts.